So welcome back everyone. In this tutorial we are going to implement our design in ADS and we'll simulate it to see how best our design suits our specification. I have already placed the models here. Okay, as you can see VT0 is given of NMOS, this is NMOS model and PMOS model. Now I'm going to make the circuit. Okay, what I'll be required, these are the two input NMOSs. One is the biasing NMOS, one is the mirroring NMOS. Okay, so I'm finished with this. I will take this PMOS, I will place the PMOS, these are going to act as mirrors. Okay, once this is done, okay, now we are going to I need to invert this, so I'll mirror it about y axis, shift y. Okay, this is okay. Again I shift y. Okay, I mirror that. Now I just need to make the connection, but before making connection, you can see here this ADS gives actually the drain and source should be symmetrical, but ADS specifies source. So what we need to do is just flip it so that okay, even this we have to flip. Okay, we need to flip this as well. Okay, once it is done, now we need to make the connections. Choose this wire. Okay, first thing you need to do is connect the source and drains. Connect source and body. Okay, we do this in order to avoid the body effect. Okay, body is not connected to source, then it is going to body is going to be at some other potential. So what it will do is it is going to change the threshold voltage, is going to have an impact on the threshold voltages. So therefore the first thing we in this design is to connect your gate to your sources. Okay, even for the stop. Now I need to connect both of them. Okay, once this connection is finished, I need to place power supplies. First I will place ground. Okay, and after that we have to bias the circuit using a DC current source. So here in the model I'm going to choose frequency domain sources and AC current source. I'll place that here. Okay, I need one DC source for biasing. Okay, and then I need AC sources to give input, so I'll place them here. Okay, once this is done, I'll connect this. Okay, I've connected my VDD. We have to give them values. I have not given them values yet. I'm just trying to make the circuit first. Okay, values are not yet given. So this connection connected is made. Okay, no ground is required. Okay, I'm going to place the ground here. Now I need to give one input to this terminal and the other to this terminal. So I'll place it here, and the other I'll place it here. Second input I've applied. Okay, I will ground the power supplies. Here is grounded. Okay. So now what I have to do is give values to these parameters. So what is my IDC DC current In our previous problem we have assumed it to be 100 microamperes, so I'll give that 100 microampere. Okay, similarly the width here I have given as width of W3 and W4 we got in the previous example as 20 microamperes, so I'll give that values here. And length, we assume the length to be 10 microamperes, so 10 microamperes, apply. Okay, similarly for this transistor, length is 10 microamperes. Okay, and width is 20 microamperes. Okay, now for this transistor, these are M1 and M2 transistor. For this length we have assumed to be, that means we designed it to be 260 microampere. Okay, length is 10 microamperes, 10 microamperes, apply. And width was 260 microamperes. Okay, apply. Okay, similarly for this transistor, length we got as 10 microamperes, width we assume to be 260 microamperes, apply. Okay, and for this M5 transistor, length was again the same for all the transistors, and width for this transistor was 30 microamperes. Okay, this is done, and I will ultimately 10 microampere, and width for this was 30 microamperes. Okay. So DC for this process was 5 volt. It is not like your guidance. Here you have to give all the DC values, all the parameter values, even the model values needs to be given. Okay, once this is done, select this VAC. Okay, for this VAC we will assume a millivolt of voltage, okay, 1 and 0. VDC here we will give it to be 2. Actually our ICMR range was from 1.5 to 4.5. I am giving a value in between that, it is 2 volts, apply. Okay, and similarly here you need to give the same voltage values but with a different polarity. DC is going to remain the same because DC is common. Okay, it is a common mode DC. So here, in order to produce a phase difference, I am getting 180 phase. Okay, okay, now you are ready to design. One thing is you need to take output, so I will be taking my output here, so I've just named it, close, and there this is a current mirror, so the drain of PMOS should be connected to the gate. Okay. So this is a MOSFET transistor, and here you can see model is specified here. Model is M1. For all the transistor, model is M1. So this model is not same. Okay, for NMOS transistors, MOSFET M1 is the model. For a PMOS transistor, M2 is the model. So you need to change that. Okay, I'll change it from here itself. This is MOSFET M2, and even this is MOSFET. Okay, just try to flip this. Here to the current mirror, so drain should be connected to gate. Okay, I'm done with everything. Now what I have to do is just simulate it. So I will just go into my simulation models. Okay, I want to do as AC simulation. I'll press that here. I will give a range for AC. Actually this is not going to going to let you start from 0 Hz, so therefore I am giving the input as 10 Hz. I want to go till 1 gigahertz. Okay, I just want 50 points. No matter, let the ADS decide how they are implemented. Okay. Okay, now it is finished. Just select this AC and simulate. Okay, this is the simulation window. Once it pops up, select one rectangular window, V out. We'll add that to output list, and we want in dB. Output we need in dB. So okay, so this is awkward kind of thing. Why? Because the scale is linear scale. You don't want a linear scale, you want a logarithmic scale. Select this, go to plot options, x-axis in logarithmic. Okay. So this is how you are going to get your output, right? We have forgotten to include the capacitor, load capacitor, for which we have designed. So I'm including that. I'll rotate it. Okay, I'll connect it to the output. So this is the output. Okay, once connections are made, let me ground it. And we have designed for 10 picofarad. So that is what I will put its value, and now I'll try to simulate it. Okay, once we simulate it again. Okay, so this is the result, ultimate result. Okay, the gain is slightly varying. This is because the capacitance values of the transistors are quite high compared to the air. That means are comparable to our load capacitance. Some tuning needs to be done to it, so that in order to get this gain flatted, okay, you have to just change. As of now, this is okay. This is it.